Before we dive into this explainer, I want you to just close your eyes for a second. Imagine stepping out of the rain and walking into this incredibly warm, quiet library. But as you look around, you realize this isn't an ordinary library. The books here, well, they aren't arranged by their cover colors or their size or even alphabetically by the author's name. They're actually arranged by the invisible geometry of meaning itself. Think about that. A book about winding rivers sits right next to an atlas of old maps. A thick treatise on soil science is placed perfectly next to a beginner's guide on gardening. Books of poetry rest gently beside volumes on musical rhythm. Without anyone speaking a single word, the shelves themselves are kind of telling a story. And really, this beautiful, silent organization, that is the profound mystery at the very heart of our exploration today. We're going to be unpacking Ravindra Nayak's truly remarkable book, AI Mathematics Ladder Book 10, Embeddings and Representation Learning, to figure out exactly how machines build these deeply useful hidden maps inside their artificial minds.
And that library analogy, it brings us to a really profound question. How exactly does meaning travel? I mean, think about it. How can a computer, which let's be honest at its core only understands cold, hard numbers, how can it possibly know that a phrase like exam anxiety is deeply fundamentally related to the phrase fear before tests, right? They don't share any of the same keywords, but to us, they share the exact same feeling. So how do modern artificial intelligence systems, the very ones we use every single day, build these invisible maps of understanding without actually having a human mind?
Well, let's start unraveling this in Part 1, The Library of Meaning.
Early on in the book, we meet a curious learner named Arya, and she's talking with her very patient mentor, Dr. Vector. Sitting together in that very library we just imagined, Dr. Vector explains a fundamental rule. He says, before a machine can learn from something, it absolutely must first be able to hold its meaning. But the way a machine holds meaning is, well, it's strikingly different from how we do it. As humans, we represent our world using rich sensory experiences, mental images, emotions. We instantly feel the heat of a fire or the deep sadness hidden in a song. But a machine? It represents the world using numbers, vectors, and coordinates. So, Arya asks this incredibly natural question, why can't a machine just see a word as a word? And Dr. Vector gently explains that representation is a structured substitute. Just like a recipe isn't the meal itself, but it holds the exact structure needed to recreate that meal. Or how a map is definitely not the actual city, but it perfectly guides the traveler.
Which leads us to this beautifully reflective moment in the text. It says, "The shelf did not read the books, yet it remembered a pattern. Meaning began when neighbors were chosen with care." Wow. Just by thoughtfully arranging things, you create this invisible pattern of relationships. A machine doesn't need to read a book like a human does, as long as it can arrange ideas the way a master librarian would. And that, right there, is the true essence of representation.
So that brings us naturally to Part 2, Why Neighbors Matter.
Imagine you're standing in front of a quiet museum table, and on this table, there's a clay cup, a silver spoon, a handwritten letter, and an old iron compass. Now, if someone asked you to draw lines between the objects that belong near each other, you'd have to stop and ask the most crucial question in representation. Close according to what? Arya realizes here that distance completely depends on your purpose. A spoon and a clay cup, well, they're obviously close together if your purpose is eating. But what about the handwritten letter and the compass? They're close together if your purpose is finding your way. One guides you through words and the other through physical direction. Similarity isn't some universal fixed truth. It is shaped entirely by its purpose.
And this graph brilliantly illustrates how that human intuition translates into actual mathematics. Take a look. We have user A and user B plotted here based entirely on how much they love action and sci-fi movies. When machines look at our preferences, our emotional similarity is literally translated directly into measurable geometric distance. If two people have similar tastes, their points in this mathematical space are physically sitting right next to each other. Distance literally becomes a measure of difference.
Let's expand on that in Part 3, The City Map of Ideas.
So you might be wondering, how does a machine handle something much more complex than just two movie genres? What if there are dozens of different traits? Well, it uses dimensions. Now, don't let that word scare you. Dimensions are really just different directions along which something can vary. Think of them exactly like the north-south or east-west streets on a city map. Age 25, income 50,000, purchases 12. When you arrange ordinary traits like this, they just become a simple list of numbers. They become a highly precise address in a multidimensional city map. So instead of a vague, wordy description of a shopper, we now have a specific, undeniable numerical coordinate.
And the absolutely crucial point here is how this exact information translates into space. When you draw an arrow to a specific point, you remove all human ambiguity. The machine isn't looking at a person with a certain income and age, it's looking at a spatial relationship. It sees pure, raw information that it can instantly compute, compare, and understand.
Now, when you plot thousands or even millions of these points, something truly magical starts to happen. These beautiful clusters naturally begin to form in the space. When many similar points gather together, patterns just naturally emerge. Nobody had to explicitly go in and label them. The machine can just see, plain as day, that this blue group of points behaves one way, and that green group over there behaves another. It's literally the visual discovery of pure knowledge.
Which leads us directly into part 4, when meaning becomes distance.
Okay, so we've mapped movies and we've mapped user traits. But what about human language? How can the abstract, poetic feeling of a word possibly be turned into structured math? The elegant truth of modern AI is found right here in word vectors. Just look at this visual equation. King minus man plus woman equals queen. No way, right? But it works mathematically. Why? Because during training, words that appear in similar contexts slowly drift closer together in this geometric space. The machine actually learns profound human concepts like gender, royalty, or power simply as directions in space.
Meaning literally becomes measurable. It's a beautifully humbling realization, isn't it? Machines do not understand language the way you or I do. They don't feel the rich history or the warmth behind a word. But they perfectly, flawlessly understand its location, its mathematical distance, and its neighborhood. Let's ground this in reality for a second. Part 5, the recommendation table.
You might be asking, how do massive systems like Netflix or Google actually use these invisible maps every single day when you're just sitting on your couch trying to find a good show? Imagine this simple coordinate vector, 8, 2, 6. Let's say this represents a movie. It's an 8 on action, a 2 on romance, and a 6 on comedy. When you watch that movie and you enjoy it, your personal digital profile simply moves a tiny bit closer to that specific coordinate. The system is just storing your point and quietly computing the mathematical distance between you and millions of other movie points.
And the practical applications of this are absolutely everywhere. We're talking Netflix movie matching, Google semantic search, ChatGPT retrieving the exact right context to answer your prompts, or even a bank identifying weird, anomalous data to stop credit card fraud. Whenever artificial intelligence recommends your new favorite song or finds the perfect answer to a question, it's not performing magic. It is simply taking a walk toward the right neighborhood in its vast vector space. It's just finding the closest geometric neighbor to whatever it is you need in that moment. And finally, we arrive at part 6, the hidden shape of memory. Let's return just for a moment to that warm, rain-tapped library we started in. Let's think about the true, overarching purpose of representation learning. Dr. Vector tells Arya something incredibly wise here. He says, a powerful tool can still be the wrong tool. Representation is useful for getting and useful remembering. You see, embeddings are fundamentally a design choice. By turning this incredibly rich, chaotic world into these neat mathematical coordinates, the AI is intentionally compressing reality. It is intentionally choosing to forget the noise, preserving only the essential relationships that actually matter for the specific task it's trying to solve.
Embeddings are not mysterious anymore. They are literally just the shape of memory. Modern AI is really just trying to beautifully, mathematically organize meaning. And I think that leaves us with an incredibly provocative final thought. The next time a machine seems to perfectly understand your deepest, most complex question, just remember, it isn't reading your mind. It's just finding your coordinates. What else in our rich human experience could be mapped, measured, and understood if we just found the right dimensions? Think about that the next time you use an AI. Keep learning and keep wondering.